Now let us consider the case where matrix A has repeated eigenvalues. So we are doing x prime equal to A times x, a 2 by 2 matrix. Assume that it have repeated eigenvalues lambda. So lambda 1 equal to lambda 2 equal to lambda. There are two possibilities. The first one, so they are this lambda 1, lambda 2 equal to lambda's real number. So two possibilities. Matrix A is diagonalizable. In this case, lambda corresponds to this lambda. We have two linearly independent eigenvectors, or we have only one linear independent eigenvectors. So this means that lambda is defective. The matrix A is not diagonalizable. Lambda is defective. In this case, with one actual eigenvector, you find another one. We need one generalized eigenvectors. So let's consider this two cases. The first case where we have two independent eigenvectors. Say two eigenvectors are case 1 v1 and v2. The plane x1 x2 this plane. Assume this v1 is these vectors correspond to this v1. We have one eigenspace here. So the line L1 corresponds to v1 lambda 1. Actually there's only one lambda here. It's repeated. We are real eigenvalues. Assume that real number is say positive, lambda positive. The case negative should be similar. Lambda positive. Consider this case. Lambda positive, therefore on this line just go out. V2 also going outward here because it corresponds to lambda positive. V2 same lambda positive. So you see that the solution x t is c1 v1 e lambda 1t is lambda t, c2 v2 e lambda 2t, e lambda 2 equal to lambda. So lambda is the same. Lambda is the same, the two are the same. Therefore, it's just something times v1 plus another scalar times v2. Neither of them dominates the other. So any combination of those red and green give us a vector like that. Or here, there. That's why other trajectories is just go up infinity from the origin and we can go in different direction depend on the combination C1, C2. So the general pictures should look like this. Each one light here corresponds to one solution. All of them go off infinity because the two main ones go off infinity. In this case, the origin is a source. This is a node, so nodal source, and this is proper. Yeah, each one of them is on line. They don't share the same tangent line. So this is the easiest case for repeated eigenvalues. For the case lambda negative, the only difference is that we go inward the origin. It's going to be a sink instead of a source. Now consider K2 where lambda is defective. K2 lambda is defective. We have one actual eigenvectors v1. So for now, let me just use v. We need to rebuild that v1 anyway again. V, the actual eigenvectors, correspond to lambda. Now we try to find the generalized eigenvectors. It is solution of the equation a minus lambda I square. We are doing the rank 2 generalized times v2 equals to 0. We know that this is defective, so we are supposed, if it is not defective, if it's complete, we should have 2 independent eigenvectors, but we are missing one. When we raise power 2, it will be 0. It's always like that. So this one is actually 0 matrix times v2 equal to 0, vector 0. So v2 can be any vectors, but it's a generalized one, so it's not the actual eigenvectors. So we can choose v2 so that v2 is independent from v. Let me say v can be something, v2 to v2 independent from v. So for example, we choose v2 to be 1, 0 or 0, 1 depending on v. So v2 independent, linearly independent from v. Now from v2 you contract back, you get v1. v1 is computed at a minus lambda I times v2. This one is non-zero. It is an actual eigenvectors. If this is 0, then v2 is an eigenvector. So we are, the only reason we choose v2 independent from v1 so that v1 is non-zero. We have one actual one. This is an eigenvectors correspond to lambda, and v2 is a generalized one. The general solution of x prime equals to a times x is of the form xt c1 v1 e lambda 1t, so is lambda t plus c2 times the generalized function, so c2 times v1t plus v2 e lambda t. So here we have a general solution. Now let's sketch the solution curve. We see that E lambda t is in common. E lambda t inside C1, V1, C2, V1, t, and C2, V2. So let's sketch for an example. In case the actual eigenvectors V1 is -3, 3. V2, the generalized one, the actual eigenvectors. V2 generalized one, 1, 0. Eigenvectors, lambda, the eigenvalues, say eigenvalues 4. x1, x2 give us this axis. x1, x2, lambda of V2, V1 -3, 3, -3, 3. So give us this line. Second one, the V1 is actually the x-axis, x1 axis. Lambda equal to 4 along the red one. Lambda equal to 4 positive, the red one, V1, the actual one. The solution go of infinity is lambda 1 tend to infinity. In this case, without even arguing a lot, we know that this case is like almost spiraling, but it's blocked by this the actual eigenvalues line. So either going clockwise or counterclockwise, like this, or the other way. So to determine that, pick one point, check, pick 1, 0, 1, 0, and look at the matrix. Assume that we have the matrix A 1, 3, -3, 7. So 1, 3, -3, 7 multiply this 1, 3, -3, 7 and give us the first column 1, 3, 1, 3, both positive, so it should pointing up. The solution curve should look like go from origin, follow this, go of infinity. Now we can draw a few other. The other side is opposite. So we only see this type of behavior when we have one actual eigenvectors with a defective positive eigenvectors. In this case, this is a a node, it is a source because everything going out. Origin is source, nodal source. This is improper because it's the own tangent to V1. If we really want to understand it, why parallel to V1, you see that here's one case. If C1 bigger than 0, T is bigger than 0, T tends to infinity. This term tends to infinity. This one is so big compared with the other two without any T. So the dominant one is V1. That's why parallel to V1. About the case where say T negative, infinity, assume that C2 still positive, this one will be negative. Negative V1 plus just something, just some numbers times V2. So we still go to the direction of opposite side of V1. So V1, so you go up like that, V1 is minus 3. Opposite side of V1 is this side. That's why we see this behavior. Similarly, you can do the same thing for the case where lambda is negative. Lambda is negative,